Hello. Um, so, welcome back. This is another example on how to do a relative motion analysis to determine an acceleration of a point. Um, in this problem, I apologize for my clumsy image. It's supposed to be a 45, 45, 90 right triangle. The idea is this: there are two ramps. They're supposed to be perpendicular to each other, and then there's a rod with two rollers on either end. And the rollers are going to roll along the respective surfaces, and we are given the speed and acceleration of point A, and they're both going down the ramp. And we're supposed to use those to determine the, let's see here. We are going to use those to determine the angular acceleration of rod AB and also the acceleration for rod AB. So we want to find alpha, and we want to find the acceleration. Sorry, we want to find alpha for rod AB, and we want the acceleration of point B. So we want alpha AB and the acceleration for point B. Okay, so to do this, let's see. Well, let's go back to something we know is true. We know to find the acceleration of B, we want to anchor that and leverage our knowledge of point A. So we're going to use a relative motion analysis. We're going to find the motion of B relative to A. So we'll say that the absolute acceleration of B is the absolute acceleration of A as a vector statement. Up here, I just had the magnitudes. And then I have to work out the relative acceleration portion, and that's going to have a tangential term. Minus the centripetal term. Right, B relative to A. Okay, so let's kind of go through a checklist here. What are the things that we have or could easily get? Well, the rod is initially horizontal, even though my diagram's a little bit skewed. So we know at the start, we know that RBA, so the position of B relative to A, is simply going to be 10 meters x hat. And it's in the positive direction, because if you're standing at A, you would look to the right to get to B. And the other thing we can work out is what is the acceleration of A. We want the acceleration and velocity of A at the start to both be down. So I know this is the magnitude of the acceleration, and it has to be pointing down, so it has to be parallel to the ramp. So that means that I can write the acceleration of point A is 3 meters per second squared times, and it's going to be to the right and down. So that's going to be x hat minus y hat divided by the square root of 2. Okay, because it follows that 45-degree line going down with negative slope. Okay, so let's kind of underline the things that I know. I think I'm using Zoom's features, and it doesn't have quite as many little features. There we go. So in green, Let's see, what are the things we know? We know the acceleration. We know the relative vectors. Okay, what are the things that we're going to have to actually work to find? We need to find omega, and we need to find alpha. Well, omega, at least we have a method for that. So I'm going to kind of underline that in yellow. That's kind of not quite for free, but something we at least have a standard trick to getting. And then we have to worry about finding alpha. But let's remember, alpha only has one non-zero component. So really there's just one number here. And the acceleration of point B has to be along the ramp. So really it can only move in one dimension. So really there's only one number there. So after you find omega AB, there are really only two unknowns, and this is a vector equation which gives you two component equations. So ultimately we have two equations and two unknowns. So our plan is this. We're going to first find omega AB, and to do that I'm going to use an instantaneous, I want to use a black color there. I'm going to use an instantaneous center of motion analysis to find omega AB. And then once I have that, I'm going to use that omega AB and all the other information to work out the acceleration of B and alpha AB. Okay, so that's the plan of attack. Okay, so let's go through that. I have my ramp here, and I have point A, and I have point B, and I know that A is moving this way, and I know that B is moving this way, and if I were to draw in the lines of action, which are perpendicular to their velocities, for A, it would be kind of going up this way on a 45-degree line. And for B, it would be going up this way on a 45-degree line. And that is going to be my instantaneous center of motion. So that's the point.
Dad, everybody's going.
That's the point about which, that's the point about which the rod and rollers are undergoing a pure rotation in that instant. So that lets me say immediately that, well, I would say that VA equals omega vector cross RA IC, but I can see from the picture which way it's going. So really all I care about is the magnitudes of this thing. So I'm just going to take magnitudes, and that's going to tell me that the magnitude of VA equals this distance. So that's going to be times omega. So omega times R A C. And this is the magnitude of this guy. Now, because these are 45-degree angles, and I know that the hypotenuse here of this triangle is 10, I know that this number is 10 divided by the square root of 2. And the square root of 2 is 0.707, so this should be 7.07. Okay. Okay. All right. Sorry, if you can hear my kids, they're currently pushing each other. That's great. Top flight parenting this. All right. Back to the problem at hand. So that allows me to rework this and say that omega equals, well, the velocity at point A was 2 meters per second. At least the speed of it was, the magnitude of it was. and I want to multiply by the square root of 2 and divide it by 10 meters, which all told, when you work it all out, then is going to give you 0.28 radians per second for omega. And you can look at this and see that it wants, at that instant, omega will be a positive quantity because they're kind of moving, swirling around that center of motion with a counterclockwise rotation. Okay, so now we know omega, and I can write it as a vector if I want. I can say omega vector is, well, I guess I don't even really need that. Okay. So let's go back. Let's keep track of where we've been. So this one is now done. So I can make that green. Done. And now I just have to write this out and do the algebra to solve for the things that I don't know. All right, so I'm going to go to another page here. So I want to write down the back to black. The acceleration of B equals the acceleration of A and then I have the tangential term, which is plus alpha cross, I was writing it out symbolically, cross RBA minus omega squared RBA. Plugging in the numbers and the things that I know that this, look at the picture, the acceleration of B must be along the ramp. So that means that the acceleration of B, the vector, must equal its magnitude, or not magnitude, just the component, I guess, in the direction along the ramp. So that would be x hat plus y hat divided by the square root of 2. All right, so this is going to be the acceleration of B times x hat plus y hat divided by the square root of 2 equals the acceleration of A. That was 3 times, and it was x hat minus y hat divided by the square root of 2, minus because it was going, point A was going downhill, plus, so alpha points in the z direction, r points in the positive x direction, z cross r is y, so that positive y, so that's going to be alpha times 10, because r had length 10, times y hat, and they get minus omega squared. Well, omega was 0.28, so omega squared is 0.078. So that's going to be 0.0784. I may have lost some digits there with rounding, but close enough. Times 10, coming from here, x hat. All right, so very good. Now, let me rewrite this just a little bit. Let's write this as x hat times 3 over root 2 minus 0.784 Yeah, that's okay. Plus y hat times, I have 10 alpha minus 3 over root 2. All right, so now we need to solve this. And you can do it. You can write out the components. You know, an easy way to do this, or slightly easier way to do this, is to say that the left-hand side, whatever it is, has equal, the x and y components have to be the same. That means that these two quantities in parentheses must be equal to each other. So I could rewrite that to say 3 over root 2 minus 0.784 must equal 10 alpha minus 3 over root 2. Turn that around, you can say alpha equals 1/10 of 6 over root 2 minus 0.784 in parentheses. If I type all that in, I get 0.1 times 6 divided by 2. And I find 0.34, oh dear, right on a diagonal, 0.346 radians per second squared. And I may be a little bit off. I may have rounded a little bit. I'm kind of worried about the value I had for omega, that I only had 2 digits there. All right. Once we have alpha, then we can go back up here and plug in, and you can use well, really, you could use just the x component. You don't even need alpha to find that. So the x component here must equal the acceleration of b divided by square root of 2. So we get that the acceleration of point B, the coefficient, is square root of 2 times this quantity. So when I type that in, when I work it out, I get 1.89. Okay, so that gives us the angular acceleration of the rod AB, and it gives us the I guess really it's the magnitude of the acceleration of point B. For this setup. All right, so that's the end of this example. I'm going to post a couple more examples. These relative motion problems, conceptually they're not very complicated, but algebraically it can be a little tedious sometimes. So just practice. That's the main method for learning this stuff.